Hello students, myself Nimesh Prabhakar. Welcome to Process, Dynamic and Control lecture series. In my previous lecture, I start chapter number 5, Basic of Distillation Column or Dynamic Behavior of Distillation Column. So in that lecture, we saw the distillation column, that means how distillation column works, what is distillation, what are the steps of distillation process, and which are the components involved in the distillation process. Now, in this lecture, we discuss about the steady state model, and in that we discuss the material balance and energy balance. So, in this lecture, we discuss the material, that means the mass balance and energy balance of distillation process. So now we start steady state model. The first step in design of control system must be the development of process model. That means this is the essential step of any control system, because by using the process model we can by using this process model, we can predict the output of the system. So it is a very essential step of any system. Frequent omit in a simple distillation column. This step is essential to minimize the need for field reconfiguration of control strategies. The model defines the process with equations developed from a material and energy balance of the unit. Now we start with the material balance, that means mass balance in the distillation process. See, this is the basic diagram or the figure of distillation process. So here you can see this is the F indicate the feed material and D indicate the distillation, that means we get the product from the overhead section, and B indicate the this is the bottom section. So here the F is the feed rate, and we can also say this is the inlet flow, and D is the overhead rate, and we can say as a distillation product and outlet flow, and B is the bottom rate, and we can say it is also the outlet flow. So the F is the inlet and D and B are indicate the outlet. Percentage LKF indicate the light key in the feed. Percentage LKD indicate the light key in a distillate product, and percentage LKB indicate the light key in the bottom product. So these are the this is the material balance figure. Now from the figure we can write F is equals to D plus B, of course, because the inlet is F and we get the distillation and bottom product. So we can write F equals to D plus B. Now according to the material balance, we know the equation is accumulation is equals to inlet flow minus outlet flow. So here the accumulation is equals to, we can write inlet flow is F and outlet flow is a summation of D plus B. So we can write the accumulation is equals to F minus D plus B. At steady state, accumulation is 0. We know at the steady state there is no change. So at that time accumulation term is become 0. So we can write equation number 2 as inflow is equals to outflow So we can write F is equals to D plus B or D is equals to F minus B. And now we give this equation as a equation number 4. So this is the basic material balance of distillation column. Now material balance of light key component. F percentage LKF is equals to D percentage LKD plus B percentage LKB. So this KF, this LKF is a light key of feed and LKD indicate the light key of distillation and KB is indicate the light key of the bottom. So we can write instead of D as a F minus B from the previous equation. So simply here we substitute instead of D is equals to F minus B. So we get F percentage LM is equals to F minus B into percentage LKD plus B percentage LKB. Now we simplify this equation. That means F multiplied by LKD minus B multiplied by the percentage LKD and remaining term is 7. So now we can simplify this equation as that means from the left hand side we take F as common and the right hand side we arrange the equation as we take common. So finally we get the equation as B upon F is equals to percentage LKF. Here the F is the subscript minus percentage LKD, D is also subscript, percentage LKB minus percentage LKB. So this is the ratio of the B upon F, that means bottom to feed. Now in the most general case, the feed might have 4 components. Having the concentration of LLKF, LKF, HKF and HHKF. 3 of these components appear in each of the bottom and overhead product. This separation of the column is fixed by the specifying the heavy key component in overhead product HKD and the concentration of light key component in the bottom product LKD. And here this LLKF indicates the lighter than light key in the feed. LLKD is indicate the lighter than the light key in the distillate product, and this percentage HKD is indicate the heavy key in the distillate product. Now, if the composition of the feed, distillate product and bottom product are known, then component material balance can be solved. 100 is equals to percentage LLKD plus percentage LKD plus percentage HKD. Now we can write this equation as D into percentage LLKD is equals to F percentage LLKF. And finally we can write as F is equals to percentage LKF is equals to D percentage LKD plus B percentage LKD. Equation number 8 and 10 assume to heavier than heavy key is found in the distillate and that no lighter than the light key is found in the bottom. So the rearranging equation number 10 gives percentage LKD is equals to F into percentage LKF minus B into percentage LKB divided by D. And substituting the equation number 4 into equation number 9 and 11 gives percentage LLKD is equals to F into percentage LLKF into F minus B. So instead of D, we write F minus B. Percentage LKD is equals to F into percentage LKF minus B into percentage LKB upon F minus B. Now substituting equation number 12 and 13 into equation number 8 to eliminate percentage LLKD and percentage LKD. So we get finally B by F is equals to 100 minus HKD minus percentage LLKF minus percentage LKF upon 100 minus percentage HKD minus percentage HK. So this is the equation for the material balance. Now we start the procedure for the energy balance. So the energy balance and the separation octane are closely related. Conceptually, product composition control can be though of the problem of the rate of heat addition QB at the bottom of the fractionator and the rate of the heat removal QT at the top of the column. Figure show the steady state internal model of this equation. The vapor boil-up rate VB equal the heat QB and by the reboiler divided by the heat of vaporization delta H of the bottom product. So we can write the vapor boil-up rate VB is equals to QB upon delta H. And the vapor rate V above the feed rate equals the vapor boil-up plus the vapor entering visual feed. So we can write the V is equals to VB plus F into VM. Now the internal reflux rate, that is the liquid at the top tray of the column, is derived by the heat balance around the top of the tower. Assuming the steady state heat balance where the heat into the tower equals the heat out, so we get the we can write energy balance by using this equation. That means D into delta HD plus CPV plus TI plus LI into delta H LF plus CPB I plus TI plus L into CPL plus TR is equals to D into delta HD plus CPB into T0 plus L into delta HL plus CPL into T0 plus LF plus CPL into T. So this is the energy balance equation when we consider the heat into the tower equal the heat out. Here the CP indicates the specific heat, TO indicates the overhead vapor temperature, or we can say the vapor at its dew point. L indicates the external reflux, TR indicates the external reflux temperature, L indicates the internal reflux, and TT indicates the top tray temperature. That means liquid at bubble point. Now, equation 3 reduced to, we get D into CPD into TT minus T0 plus Li into delta H Li minus L into delta HL plus C into CPL into TR minus T0 equals to 0. So now we give this equation as equation number 4. So making a simplifying assumption that the tray temperature equal overhead vapor temperature, so we get equation as Li into delta HLF plus is equals to L into delta HL plus L into CPL into T0 minus Tr. Or we can write this equation as Li upon L is equals to delta HL upon delta Li into 1.0 plus CPL delta HL T0 minus Tr. Resulting in equation LPL upon L is equals to K2 into 1 plus K1 into TPO minus TPR. So now we give this equation as equation number 7. If the total condenser is employed, the composition of internal reflux and external reflux are the same. So the constant K2 is equals to 1.0, thus the equation becomes L equals to Li upon 1 plus Ki T0 minus Tr and Za is equals to L into 1 plus Ki into delta. So this is the energy balance equation. The liquid rate Lf below the feed rate equal the internal reflux plus the liquid in the feed. So we can write Lf is equals to Li plus 1 minus Vf into M. And the distillate rate D equal the vapor rate V above the feed rate minimize the internal reflux. So we can write D is equals to V minus L. And finally, the bottom rate V equal the liquid rate L minimize the boil up. So we can write V is equals to L minus Vb. So this is the energy balance equation. So in this lecture, we discussed about the steady state model and we discussed in that material balance, that means mass balance and energy balance equation. Thank you.